Hello student, this is Usha from G.k.jain High Secondary School. Today we are going to see the optics part 9 in 12th standard physics. Today we are going to learn about the polarization. 12th standard physics optics part 9 polarization. The phenomena of polarization distinctly prove that light wave are only transfers in nature. Light is propagated in the form of electromagnetic waves. The phenomenon of restricting the vibration of light to a particular direction perpendicular to the direction of propagation of wave is called polarization of light. So the phenomena strictly prove that they moving only transfers in nature. Second one, the plane polarized light. A transverse wave which has vibration in all direction in a plane perpendicular to the direction of propagation of wave is said to be unpolarized light. If the vibration of the wave are present in only one direction in a plane perpendicular to the direction of propagation of the wave is said to be polarized or plane polarized light. So let us explain this by a diagram given here. So let the incident light contain both plane polarized light and unpolarized light together. So the plane containing the vibration of the electric field vector is known as plane of vibration ABCD. The plane perpendicular to the plane of vibration and containing the ray of light is known as plane of polarization EFGH. So it's given as consolidated few characteristics of polarized and unpolarized light. So the first we'll say about the polarized light consists of waves having their electric field vibration in a single plane normal to the direction of ray, asymmetrical about the ray direction. It is obtained from unpolarized light with the help of polarizers. When we talk about unpolarized light, consists of wave having their electric field vibrations equally distributed in all directions normal to the direction of ray, symmetrical about the ray direction, produced by conventional light sources. Then we'll talk about polarization techniques. So the unpolarized light can be polarized by several techniques. We are going to discuss 4 methods. One is polarization by selective absorption, polarization by reflection, polarization by double refraction, polarization by scattering. First we will talk about polarization by selective absorption. Selective absorption is a property of a material which transmit waves whose electric field vibrate in a plane parallel to a certain direction of orientation and absorb all other waves. The Polaroids or polarizers are thin commercial sheets which make use of the property of selective absorption to produce an intense beam of plane polarized light. Selective absorption is also called as trichorism. So tourmaline is a natural polarizing material. Polaroids are also made artificially. It is discovered that small needle-shaped crystal of quinine iodosulfate have the property of polarizing light. A number of these crystals with their axes parallel to one another packed in between two transparent plastic sheets serve as a good Polaroids. Recently, new type of Polaroids are prepared in which thin film of polyvinyl alcohol is used. They are colorless crystals which transmit more light and give better polarization. This is explained in the diagram. Instead of weaving directly, they fall and then they fall on any light parallelly polarized in the horizontal plane by reflection. Then it is transmitted. So without that is glare, we are able to see it properly. The sunglasses. Polarizer and analyzer. Second one, that is in this the point. Let us consider an unpolarized beam of light. The vibrations can be in all possible directions, all of them being perpendicular to the direction of propagation. When the light passes through Polaroid P1, the vibrations are restricted to only one plane. The emergent beam can be further passed through another Polaroid P2. If the Polaroid P2 is rotated about the ray of light of axis, for a particular portion of P2 the intensity is maximum. Then the polarized P2 is rotated from this position, the intensity starts decreasing. there is a complete extinction of the light when P2 is rotated through 90 degrees. So on further rotation, the light reappears and the intensity increases and become a maximum for the further rotation to 90 degrees. The light coming out from the polarized P1 is said to be plane polarized. The polarized which plane polarize the unpolarized light passing through it is called as polarizer. The Polaroid, which is used to examine whether a beam of light is polarized or not, that is in P2, is called as your analyzer. If the intensity of the unpolarized light is I, then the intensity of plane polarized light will be I by 2. The other half of intensity is restricted by the polarizer. Plane and partially polarized light. In plane polarized light, the intensity varies from maximum to 0 for every rotation of 90 degrees of the analyzer. In the first diagram, it is shown here. Then, the vibrations are allowed in one axis and completely restricted in the perpendicular axis. On the other hand, if the intensity of light varies between maximum and minimum for every rotation of 90 degrees of the analyzer, the light is said to be partially polarized, that is shown in the second diagram. This is because the light is not fully restricted in that particular axis, which shows in a minimum intensity. By using this one, we are going to explain Malus law. So, E.N. Malus discovered that when a beam of plane polarized light of intensity I0 is incident on an analyzer, the light transmitted of intensity I from the analyzer varies directly as the square of the cosine of the angle theta between the transmission axis of polarizer and analyzer. This is known as Malus law, and it is given by the equation I is equal to I0 cos square theta. So, the proof of Malus law. Let us consider a plane of polarizer and analyzer are inclined to each other by an angle theta. Let I0 be the intensity and A be the amplitude of the electric vector transmitted by the polarizer. Let the amplitude A of the incident light has two rectangular components. One is A cos theta, another one is A sin theta, which are the parallel and perpendicular component to the axis of transmission of the analyzer. The component A cos theta will be transmitted by the analyzer. The intensity of light transmitted from the analyzer is proportional to the square of the component of the amplitude transmitted by the analyzer. Then we have the equation I is proportional to A cos theta whole square. So to remove the proportionality, introduce a constant. So we'll get I is equal to K into A cos theta the whole square. Then we'll get I is equal to K A square cos square theta. I is equal to I0 cos square theta, where I0 is equal to K A square is the maximum intensity of light transmitted from the analyzer. Here we have two conditions. When theta is equal to 0, cos 0 value is 1, so I is equal to I0. When the transmission axis of the polarizer is along that of the analyzer, the intensity of light transmitted from the analyzer is equal to the incident light that fall on it from the polarizer. Case 2, when theta equal to 90 degree, cos 90 value is 0, then I will be equal to 0. When the transmission axis of polarizer and analyzer are perpendicular to each other, the intensity of light transmitted from the analyzer is 0. Then we go to the next topic, uses of Polaroids. Polaroids are used in Googles and cameras to avoid glare of light. They are used in three-dimensional motion picture, that is in holography. Polaroids are used to improve contrast in old oil paintings. They are also used in optical stress analysis. It is used as a window glass to control the intensity of incoming light, where they are used in your aeroplanes. Polaroid laser beam act as needle to read, write in compact disc. Polaroids produce polarizing light to be used in liquid crystal display, LCD. Next is polarization by reflection. The simplest method of producing plain polarized light is by reflection. So this is we can explain by using Brewster's law. Consider a beam of unpolarized light AB is instant at any angle of the reflecting glass surface XY. Vibration in AB, which is parallel to the plane of the diagram, is shown by the arrow. The vibration which are perpendicular to the plane of the diagram and parallel to the reflecting surface is shown by the dotted lines. A part of the light is reflected along BC and the rest is refracted along BD. On examining the reflected beam BC with an analyzer, it is found that the ray is partially plane polarized. When the light is allowed to be instant at a particular angle, the reflected beam is found to be plane polarized. The angle of instant at which the reflected beam is plane polarized is called polarizing angle IP. So, according to Brewster's, when ordinary light is instant on the surface of a transparent medium, the reflected light is partially plane polarized. So the angle of instant which a beam of unpolarized light is falling on a transparent surface is reflected as a plane polarized light is called polarizing angle or Brewster's angle. It is denoted by IP. Now we can say that Brewster found that the instance of polarizing angle, the reflected and the transmitted ray are perpendicular to each other. Suppose IP is the polarizing angle and RP is the corresponding angle of refraction. Then we can write IP plus 90 degree plus RP equal to 180 degree. So RP will be equal to 90 degree minus IP. From Snell's law, the refractive index of the transparent medium is sin IP divided by sin RP is equal to N, where N is the refractive index of the medium with respect to R. Then we have substituting the value of RP from equation, we get sin IP divided by sin of 90 minus IP, which is equal to sin IP divided by cos IP, which is equal to N. So we'll get sin by cos is tan. So tan IP is equal to N. This relation is known as Brewster's law. The law states that the tangent of the polarizing angle for a transparent medium is equal to its refractive index. The value of the Brewster's angle depends upon the nature of the transparent refractive medium and the wavelength of the light used. Under the polarization by reflection, the next topic is pile of plates. So it consists of number of glass plates placed one over the other in a tube. The plates are inclined at an angle of 33.7 degree. That is the diagram it is shown. So that is 90 minus 56.3 degree to the axis of the tube. A beam of unpolarized light is allowed to fall on the pile of plates along the axis of the tube. So the angle of instant light will be at 56.3 degree, which is the polarizing angle for glass. The vibration perpendicular to the plane of instant are reflected at each surface and those parallel to it are transmitted. The larger the number of surfaces, the greater is the intensity of light reflected, plane polarized light. The pile of plates is used as an polarizer and also they are being used as an analyzer. Next we'll go for polarization by double refraction. When a ray of unpolarized light is instant on a calcite crystal, two reflected rays are produced. Hence, two images of a single object are formed. This phenomenon is called double refraction. Double refraction is also called birefringence. This phenomenon is also exhibited by several other crystals like quartz, mica, etc. So let us take a paper and keep an ink dot on it. And then a calcite crystal is placed on it. So we are able to see two images on it. On rotating the crystal, one image remains stationary while the other rotates around the first. The stationary image is known as ordinary image O, produced by the refracted ray which obey the law of refraction called as ordinary ray. The other image is called as extraordinary image E, produced by the refracted ray which do not obey the law of refraction called as extraordinary ray. The extraordinary ray is found to be plane polarized. So now we are able to see the diagram. Inside a double refraction crystal, the ordinary ray travels with the same velocity in all directions and the extraordinary ray travels with a different velocity along different directions. If a point source inside a refracting crystal produces spherical wavefront corresponding to ordinary ray and elliptical wavefront corresponding to ordinary ray. So there is a particular direction in which both the rays travel with the same velocity. This direction is called optical axis. Along the optical axis, the refractive index is same for both the rays, and there is no double refraction along this direction. This will happen inside the crystal. Next, there are two types of optically active crystal. Crystal like calcite, quartz, tourmaline, and ice having only one optic axis are called as uniaxial crystal. Crystal like topaz, selenite, and aragonite having two optical axes, and they are called as biaxial crystals. Next is nickel prism. Nickel prism is an optically device incorporated in optical instruments both for producing and analyzing plain polarized light. The construction of nickel prism is based on the phenomenon of double refraction. One of the most common form of the nickel prism is made by taking a calcite crystal, which is double refracting crystal, where its length is 3 times its breadth. ABCD represents the principal section of a calcite crystal. It is being cut into 2 halves along the diagonal so that the phase angles are 72 degree and 108 degree. They both are joined by a material called as Canada balsam, a transparent cement. Let us consider a ray of unpolarized light from monochromatic source such as a sodium vapor lamp is incident on the face of AC of the nickel prism. Double refraction takes place and the ray is split up into ordinary and extraordinary ray. They travel with a different velocity. The refractive index of the crystal for the ordinary ray is 1.658 and for extraordinary ray is 1.486. The refractive index of Canada balsam is 1.523. Canada balsam does not polarize light. The ordinary ray is totally intent reflected at the layer of Canada balsam, and it is prevented from emerging from the other face. The extraordinary ray alone which is transmitted to the crystal, which is plain polarized light. Uses of nickel prism is produces plain polarized light and functions as a polarizer. It can also be used to analyze the plain polarized light, that is used as an analyzer. Drawbacks of nickel prism. Its cost is very high due to scarcity of large and flawless calcite crystal. Due to extraordinary ray passing obliquely through it, its emergent ray is always displayed a little to one side. The effective field of view is quite limited. Light emerging out of it is not uniformly plane polarized. The next topic is polarization by scattering. So the diagram is shown over here. The light from a clear blue portion of the sky shows a rise and fall of intensity when viewed through a Polaroid which is rotated. This is because of sunlight which has changed its direction or on encountering the molecule on the Earth's surface. The instant sunlight is unpolarized. The electric field of light interacts with the electron present in the air molecule. Under the influence of the electric field of the instant wave, the electron in the molecule acquire component of motion in both these directions. When the observer looking at 90 degrees to the direction of the sun, charges accelerate parallel to not radiate energy towards this observer. Since this acceleration has no transverse component, the radiation scattered by the molecule is therefore polarized perpendicular to the plane of the person. This explains the reason for polarization of sunlight by scattering. Hi students, you all have learned about the polarization in this session. We'll meet you in the next video. Thank you.